Hi everyone, this is Nilay. This is my final project for CSCI 222 Foundations of Large Language Models Spring to 2026. My project is titled Building a Multi-Tool LLM Agent for Search, Calculation, and Code Execution. Quick agenda, I'll walk you through the problem, the architecture, we'll do a live demo, we'll go through the evaluation results, and close with limitations and future work. We'll have some discussions on key takeaways. So that's the quick agenda. Before we get into the architecture or before I show you what I've built, let me ground ourselves in why or what is the problem statement. So you see a few questions here like who is the current CEO of OpenAI? What's 47 factorial? So a pure text language model answers with whatever was true at the training time, but training cutoffs are months or years old and the model can't know its own staleness. So it answers confidently and it's confidently wrong. Similarly, with mathematical questions, it token by token text generation is structurally bad at this kind of arithmetic where you have to pick five items from 47. If the question is something like what's 47 factorial divided by 42 factorial times 5 factorial, it's like a chain of commands. So you'll get a confident looking large number from a LLM and it will be wrong. And then question three, the one that really exposes the gap, is something like a question that is shown here, which is like, what is the GDP of Texas divided by its population? In this case, the model has to recall an outdated GDP, recall an outdated population, and divide them in its head. So three independent ways to fail, stacked together, and it presents the wrong answer with the same confidence as if it had looked everything up. So the gap is with language models hallucinating facts, fumbling with arithmetic, and they can't act on the world basically. So real questions that users can pose to an LLM need all three, and a single text generation step cannot do that faithfully. So that's the problem statement that this project tries to address. Uh, Quickly, what is in scope, what is out of scope? So in scope was reliable tool selection, faithful execution, full observability through structured tracing, reproducible evaluation with committed artifacts, and basic safety through input validation. Out of scope was fine tuning. Pre-trained Claude model that I use is already excellent at tool use. RAG, I did not do that because search via Tavily API is simpler and covers the factual queries, multi-turn memory. Each query, I haven't implemented multi-turn memory. Each query is independent, which keeps the eval clean. I don't have an hardened sandbox. The code execs a process timeout is good enough for an academic project. Production grade Docker or SecCom setup was just too much for me for the scope of this project. Next, the approach. So the model that I used was pre-trained Claude Sonnet 4.5, accessed via the Anthropic Messages API. I used this as is. I did not do any fine tuning, no adapters, no custom training data. The method was native tool use. I declare three tool schemas in JSON. The model emits structured tool use blocks when it wants to call one. The code executes the call and returns a tool result. The loop continues until the model emits a plain text answer. Three things that I did not use were no fine tuning, as mentioned earlier, no RAG, and there's no agent framework like LangChain or AutoGen. I wrote the agent loop directly. It's about 200 to 250 lines of Python. That gives me full control over tracing and full visibility into every step. Um, Next, the architecture. So here is the full architecture or a simplified version of that architecture in a single diagram. It's a single loop with three exits. A query comes in. It is sent to Claude along with uh, the schemas for the three tools that I have. Claude responds. Every response has a stop reason. If it is just text, that's the final answer. If we extract and we extract it and we are done. If it's tool use, Claude is telling me that I want to call one of these three tools that you gave me as an argument. Then my code executes the requested tool, packages the result back as a tool result block, and the loop continues. Claude sees the result, decides if it needs another tool or if it can answer, and the cycle repeats. Capped at 8 iterations, that's a safety net. If the model gets stuck in a loop, we just exit after eight iterations of the loop. Um, Three design decisions that aren't obvious from the diagram. Sorry for that. Uh, One at every step, the model call, the tool call, the result, they are all recorded in a trace object, in a Python trace object. That trace is what we cover later on. Um, Second, the eight-step cap, it prevents the model from spinning forever on a question it can't answer. And third, when a tool returns a matplotlib figure, this is a tool that I use, is a code execution tool that I use to generate plots. So when we generate images, they are stored as raw bytes, and I don't send those raw bytes as a response back to Claude uh, for efficiencies, because those bytes anyways don't mean anything to Claude as such. Um, so those are the three things I wanted to call out that are not explicitly called out in the diagram. So looking at the three tools that I have, each is a single Python function with a JSON shaped contract. Search tool uses the Tavily web search API is wrapped. It wraps that API, takes a query, returns up to 10 results, title, URL, snippet. Snippets are clipped to 500 characters, so the context doesn't get flooded with raw HTML. Calculator tool. Second is the calculator tool, which is where I spend most of the effort on safety. It parses the expression with Python's AST module, walks the tree, only permitting a whitelist of operations and math functions. I never call the eval. So if the model accidentally or otherwise passes some malicious code like import OS system or rm minus rf or something, it's rejected at pass time, not at runtime. The tests verify this explicitly. Then there is the code execution tool, runs an arbitrary Python in its subprocess with a hard timeout in a fresh time directory. It's a matplotlib aware code which, by which figures are produced by user code and are captured as base64 PNG and returned. It's a light sandbox, subprocess and timeout, not Docker grade. Good enough for the project, not good enough for production grade agents. Um, all the three tools have the same contract. Every tool returns a Python dictionary with an OK with a value of true or an OK with a value of false, but plus a structured error. The model treats errors just as another result, which means retry and fallback behavior comes for free. There is no special case logic in the agent loop for handling tool failures. That uniformity is the most important design decision on this slide. Next, I'm going to walk you through a quick demo of how my agent tool works. So here I've already logged into my directory. I've activated my virtual Python environment. I'm going to run a query like this. What is the GDP of Texas divided by its population? Um, so this is going to Once this runs, now you see the agent is talking to Claude. You can see the thinking icon going at the top. In the background, Claude is deciding which tool to call first. For this query, I expected to start with a research on Texas GDP, search for Texas population, and then a calculator to call calculator call to divide them. So here's what came back. The reasoning trace shows, I think, three tool calls, two searches followed by one calculator call, and yeah, two searches followed by one calculator. Yes, and the answer is approximately around, I think. So here is the answer. It's around $88,000, and it used about 7,500 tokens. Took about 11 to 12 seconds is what I've seen it generally take with this query. Similarly, we can ask it other questions. Without getting into those, I also want to show how I'm recording these activities. So I'm going to run a simple tail command on where I store the traces, and that's in my traces directory on a file called runs.sh. JSON-L. I'm just going to pipe this to the JSON.tool tool and then a script, and I'm going to cap it at some limited number. So here you can see the entire trace that I'm recording, and what the model did, what not. So this is what gives us the traceability. Um, every model call tool use result is captured as structured JSON. That's the data. That's the data evaluation. This is what the data evaluation and visualization layers consume. Um, so it's the same query what I ran, but it's just in the machine readable format. Coming back to my presentation, that's the end of the demo. So coming back to my presentation here, so I evaluated the agent on 40 queries. I handcrafted these for four categories, 10 in each category. Factual, which was single fact lookups, which would hit the search tool, like looking for the CEO of Open API company. Mathematical, which is pure arithmetic, should hit the calculator tool, like 17 factorial or something. Then the code execution tool should hit the code exec tool, and it plots an example is plotting a sin x basically. And then the last one was mixed, where it is multi-tool chains, like population of Texas divided by population of Wyoming. The kind of question you saw in the live, what we saw just saw in the live demo. So the four categories isolate four capabilities: retrieval, exact computation, execution, and chaining. The mixed bucket is also where I test whether the agent resists overtooling. Some mixed queries should resolve with a single search, not a chain. Tool selection is part of the eval, not just tool execution. Um, every one of these 40 runs is committed in my GitHub repo, so that a grader can actually go and look at those if it doesn't have the API keys. Both the reasoning traces, the aggregate summary JSON are in there. Um, um, Next, some metrics here. Every one of the 40 queries produced non-error answers across all four categories. The agent completed the task. The median end-to-end runtime was around, sorry for this, my presentation is going off. So every um, sorry, where was I here? So median end-to-end runtime was about 9 seconds. Longest was, I think, around 24 or 25 seconds. Completion here means the agent finished the loop and returned non-error answer. I spot checked semantic correctness for the math category, where I could verify answers exactly, and they were correct. Full automated semantic grading, checking, like for example, checking the capital of Magnolia really equals blah 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 across all 40 queries is in the future work. I haven't done that much of semantic grading. Um, so these are some of the metrics. Some visualizations or some graphs. At the top you see what the code execution tool produced when I asked it to plot the sine wave. You see the frequency of tool usage. This is just based on a few queries that I was running. At that time, it had called the calculator tool 18 times. So I have that capability inbuilt. This is again based on the traces. I can run a Python script that will generate these plots. It would also likewise generate the latency that each tool has. So the calculator tool has the lowest, and you see the other two bars for the other two tools as well here. So that's these are some visualizations that I have in the project. Lastly, wrapping up, what worked, what didn't. Three engineering practices, I guess. One, the eval is reproducible. Every trace and aggregate summary is committed to the repo. So verification doesn't cost API spend. System is observable. Every model call, tool call is recorded in a structured trace, which means metrics you saw come from real data. They are not hand curated. And then there is safety by design. The calculator parses with an AST whitelist instead of calling eval, and every tool returns the same OK or error shape, so error handling is uniform. Limitations, there are three. I think one is the obvious one is this. This is a light sandbox. It is not production grade. That was out of scope for me. It's just too much. There is no semantic grading. I called this out before too. I haven't semantic correctness is not automated for me. I have just factually checked some of the math answers, for example. Um, uh, and then there is a prompt injection risk, where search snippets reach the model context directly with no untrusted text channel. So that those are the limitations. Future work for this could be, moving from I'm sorry, my future work bullets are wrong here, but I can still cover. I can do an MCP server, I can do a production grade server, and I could also add more safety checks for prompt injection risks. Basically, that is those are the things that I could think of adding on top of it. And yeah, that's pretty much it for my project. Thank you.